Hello students, last class we learned about the basic types of aircraft engines. Today, we will learn about the performance and design indicators of aircraft engines. The performance indicators of aircraft engines include engine thrust, thrust-to-weight ratio, and fuel consumption rate. The design indicators include compression ratio, turbine inlet, gas temperature, and bypass ratio. Before introducing the performance and design indicators of the engine, let's first learn the station diagram of the single-rotor engine. The station diagram allows us to more clearly mark the parameters of different sections of the engine so that we can quickly understand which section of the engine it is through the station number. From the station diagram, we can see that station 0 represents the position far in front of the engine. Station 1 represents the compressor inlet position. Station 2 represents the compressor outlet position, or the combustion chamber inlet. Position station 3 represents the combustion chamber outlet position, or the turbine inlet position. Station 4 represents the turbine outlet position, or the tail nozzle inlet position, and Station 5 represents the tail nozzle outlet position. Next, we will learn about the thrust of aircraft engine performance indicators. Thrust refers to the force generated by the conversion of heat energy generated by fuel combustion into kinetic energy increment of the gas when the gas passes through the jet engine and is ejected at high speed. It is equal to the axial component of the resultant force of various forces acting on the inner and outer surfaces of the engine. When the tail nozzle is fully expanded and the fuel mass flow rate is ignored, the thrust can be expressed as the product of the air mass flow rate flowing through the engine and the exhaust velocity minus the entry velocity. Through the thrust formula, students can think about what methods are there to increase the thrust. The first method is obviously to increase the air mass flow rate flowing through the engine. To increase the air mass flow rate flowing through the engine, the size of the engine must be increased, which affects the weight of the engine. The second method is to increase the exhaust velocity of the engine. To increase the exhaust velocity of the engine, the temperature of the gas before the turbine of the engine must be increased. Obviously, the temperature of the gas before the turbine cannot be increased indefinitely. It will be affected by many factors, such as engine materials and cooling methods. Therefore, it is not difficult for us to find that there are various mutual constraints in the increase of engine thrust. After learning about thrust, can we only use the size of thrust to compare the performance of engines? For example, the maximum thrust of the WP-6 engine is 2,548 decanewtons, and the maximum thrust of the WP-8 engine is 9,310 decanewtons. We think that the performance of the WP-8 engine is better. This is obviously not possible. We also need to compare the weight of the engine itself. What kind of parameters can be used to compare the performance of the engine? That is, the thrust-to-weight ratio of the engine. The thrust-to-weight ratio is the ratio of the engine thrust to gravity and the ratio of the maximum thrust of the engine at sea level and the mass gravity of the engine. It is an indicator to measure the maneuverability of the engine. The greater the thrust-to-weight ratio of the engine, the better the maneuverability of the engine, and vice versa. For indirect reaction engines, the power-to-weight ratio is used, that is, the ratio of engine power to gravity. Next, we will learn the last parameter of engine performance indicators, fuel consumption rate. Fuel consumption rate is the ratio of the mass flow rate of fuel consumed by the engine per hour to the thrust or power. For jet engines that generate thrust, it indicates the mass of fuel consumed by the engine to generate 1 decanewton thrust in 1 hour, and the unit is kilograms/decanewtons h. Fuel consumption rate is an important parameter that reflects the economic performance of the engine. The lower the fuel consumption rate of the engine, the better the economic performance of the engine, and vice versa. Here, students must distinguish between fuel consumption rate and fuel consumption. Fuel consumption refers to the mass of fuel entering the combustion chamber per unit time. Fuel consumption cannot compare the fuel economy of the engine. Can students guess what color aviation kerosene is? High-quality aviation kerosene is a light yellow liquid. Next, we will learn about the design index of aircraft engines, the compression ratio. The compression ratio generally refers to the compressor compression ratio, which is the ratio of the total pressure at the compressor outlet to the total pressure at the compressor inlet. It is represented by the ratio of P2 star to P1 star, which is equal to pi C star. The engine's compression ratio has the best compression ratio and the most economical compression ratio. The best engine compression ratio refers to the compression ratio that produces the maximum work capacity of the engine. The most economical compression ratio refers to the compression ratio with the lowest fuel consumption rate. The gas temperature before the turbine refers to the total temperature of the gas at the inlet section of the first stage guide vane of the turbine. It is usually expressed as the total temperature at the inlet section of the turbine rotor. It is one of the important indicators of the technical level of the engine. The higher the gas temperature before the turbine of the engine, the stronger the engine's work capacity and the greater the thrust. Next, we will learn about a very important parameter, the total temperature of the gas after the low-pressure turbine, which is expressed as EGT, or multiplied by. Changes in the engine turbine exhaust temperature reflect changes in engine performance. Increased EGT indicates that the engine's performance has declined and failed. For example, dirty compressor blades. Bleed valve leakage failure will cause the engine's EGT to increase. If the engine exhaust temperature exceeds the specified value, it will burn the turbine components at the rear. So it is very important to monitor the engine exhaust temperature. Next, we will learn the last parameter of engine design index bypass ratio. The bypass ratio is the ratio of the air mass flow rate flowing through the outer bypass and inner bypass of the turbofan engine, also known as the flow ratio. The engine with a bypass ratio less than 1 is called a small bypass ratio engine, and the engine with a bypass ratio greater than 4 is called a large bypass ratio engine. In this class, we learned about the performance and design indicators of aircraft engines. Students must grasp the meaning of various parameters in a timely manner and learn to apply them flexibly. Thank you, everyone.